Okay, let's apply now the equal area criterion for the analysis of transient stability when the power system is affected by a three-phase short circuit. Okay. In this case, we will use the equal area criterion in order to identify transient stability if the machine is still in synchronism. And the first step is, in this case, assuming that there is no power transfer during the fault. Okay. As I explained in my class about the transient stability analysis, we need to define conditions before the fault, during the fault, and after the fault. Okay. In this case, the situation is quite interesting because in this case we have before the fault, and then we have during the fault, and then we have after the fault. Okay, we have three situations. Before the fault, this system is working in a steady state. This system is working properly fine. You can identify over there that there is a equation that defines the power that is coming from the generator going through the infinity bus bar. My students, they must be able to identify what is the impedance, and that impedance is really important because that impedance is defining what is the maximum power transfer. Okay. But then let's assume now that we have a short circuit. Okay. In this case, we are working with a three-phase short circuit. For that reason, of course, you must understand that we are using the positive sequence model. Okay, we will be using the positive sequence model for this analysis. Okay, but the fault is a three-phase fault. We are using symmetric positive sequence representation, but the important point here is where the fault is located. Well, as you can see, the fault is located at bus bar number 2. And bus bar number 2 is quite interesting because it's the connection point between the high voltage sides of the transformer to the to the transmission lines. And as you can see over there, when we have the volted three-phase fault at that point, there is an issue because the voltage at that bus bar is 0, and as consequence, there is no possibility of transmitting power during the fault. Okay. Now, this is a very interesting situation. Okay, because we have the short circuit here, and the voltage at this point is equal 0 because we are using a volted three-phase short circuit. Okay, but now the interesting thing is we are in a steady state condition here, and suddenly we have the fault. Okay, and the fault is here for some moments. Okay, and then at delta C, somebody opened the fault. The fault is extinguished. We will not discuss how the fault is extinguished, but the fault disappear. Okay. If the fault disappear, this machine will go back again to the original, because remember, this is the pre-fault condition, and this is the faulted condition. Let me clean here. Here, electrical power is 0, that is during the fault. That is during the fault. And the blue one, this one, is before the fault and after the fault. Before and after, they are equal because we are assuming that this fault appear and suddenly disappear, okay? That is what is happening there. Okay, as you can see here again, the power during the fault is 0 because we have this short circuit over here, but then at delta C, the fault is removed. The system configuration doesn't change. And because the system configuration doesn't change, the point jump into the original power angle equation, the power angle curve, and then the machine will oscillate. And if there is a stable position, a stable state, the machine will come back to the point A, okay? What I'm trying to say is, again, here we have two areas. The area A1 where the electrical power is below the mechanical power. That is the reason for this rectangle. The rectangle defining A1 is the rectangle between delta 0 and delta C, and is the top is the mechanical power 0, and here we have the electrical power. That is a pure acceleration area, a pure acceleration area. And the area A2, the area A2 is the deceleration. The fault disappear. I will not discuss why, but the fault disappear, and then the operating point jump here, and they oscillate the machine and try to come back to steady state. What I'm trying to say is there are two clear areas over there. There are two clear areas over there. One area defined by the points, the points A, B, C, and D. That is the accelerating area. That is the area A1. Okay. And the second area is the deaccelerating area. The deaccelerating area is defined by the points D, E, F, G. The area 2 is defined by the corners of that figure over there is located between the points D, E, F, G. Okay? Um, we will find stability. We will find stability if the area A1 and the area A2 are equal. If those areas are equal, we are in the good position because the system will be stable. Okay? From here and onwards, all the problem is defining those areas, okay? Defining those areas is extremely simple. Defining those areas is extremely simple, okay? The area 1, I already told you. You can see that the area 1 is very simple, is this rectangle. You don't need to use the integral, but for formalities I will do it. Is the integral between delta 0 and delta C, okay? Delta 0, delta C. The top here is the mechanical power. The mechanical power is P max 0, and the electrical power is 0 because we are doing the short circuit, okay? And the area 2 is also extremely simple. The area 2 is defined between delta C and delta max. Delta C and delta max, and you can see over here on the top, this is the electrical power, and here the points between D and G, they are defined by the mechanical power, okay? Now, what you need to do is, if we want stability, the area 1 should be equal to the area 2. And then we have here two interesting and two beautiful integrals. And now all the problem is calculus, mathematical calculus. I mean, all the problem is to obtain this angle delta C, obtain the angle delta C that allow the area 1 and the area 2 to be equal, okay? Um, I believe all my students, they have a very good bachelor degree, and they have a very strong mathematical background. I love those students that they love mathematics. I believe that they will be able to demonstrate this equation over here. This equation over here is calculating the critical angle delta C, okay? I didn't tell you, but delta C is probably the important angle here, okay? Delta max is the maximum oscillation. Delta max is the maximum oscillation, okay? But the critical angle delta C is the quite important, because if you release the fault before, this area will be smaller than that, and there is no problem. The system will be able to return to the stability. But if this angle is a much bigger, we will have problem, because that will be the critical moment to define the stability. Okay, to be honest, I must tell you, delta c received the name critical clearing angle. Delta C received the name critical clearing angle. The critical clearing angle is the angle that the largest angle that I can remove the fault and the system is still stable. I will repeat again. Critical, delta critical is the critical clearing angle. The critical clearing angle is the maximum angle that I can remove the fault and the system stay stable. Okay. To be honest, delta critical, we can use the equal area criteria, and we can get that number. Okay. But in real life, we don't use delta. We don't use the angle. And we don't use the angle because the angle is um, quite interesting to get inside a real power system. In real power system, we use protections, system protections, and those protections typically they prefer to be related with time. And in real power systems, we don't use the critical clearing angle. Instead, we use is the critical clearing time, the CCT. The CCT is a very important variable, because the critical clearing time is basically the maximum time that the disturbance can be applied to the power system without the system losing stability. Okay, that is the limit. That is the maximum time that we can put the short circuit in that case. And then if we remove the short circuit, the system will go back to stability. The maximum value, that is the critical clearing time, okay? Here, I include in this red box over there a classical equation. That classical equation is to calculate the critical clearing time based on the critical clearing angle, okay? As you can see over here, we have here the critical clearing time, TC, and is defined in terms of the critical clearing angle, okay? In real power system, we don't use this technique. In real power system, we use numerical simulations, and from the numerical simulations, we obtain the CCT, okay? However, all my students must be able to see that equation and use that equation to calculate what is the maximum, what is the critical clearing time, okay? My students that they are taking classes of protection, they must understand that the critical clearing time is one value that you must know, okay? You must know what is the maximum time that the fault can be inside the power system. Why? Because if you are using, for instance, overcurrent protections, or you are using distance protection, If you have many of those protections, you will use some time discrimination, okay? When you use time discrimination, you are inserting time delays between the relays, okay? And what is really important is that all those relays, and including all those discrimination time, all of them must be below the critical clearing time. What I'm trying to say is the critical clearing time is important from the protection point of view because all your protection must work and must trip for short circuit before the critical clearing time. All protections must trip and work before the critical clearing time. Because if you reach the critical clearing time, the system will be unstable. There is no reason for protection if those protections will work after the critical clearing time, okay? This is the first conclusion from the protection point of view. Another thing that I need that you understand is that the critical clearing time is also a tool to define the stability of your system, okay? If a power system has very short time, critical clearing time, your system is less stable than a system that has larger or bigger critical clearing times, okay? Critical clearing time is an indicator used for transient stability, okay? Well, now let me move to something a bit different. Well, it's going in the same direction, but now let me keep moving with the same problem, but let modify a bit the problem, okay? Now we will use again the equal area criterion, but instead of having a three-phase fault on the bus bar number 2, what we will do now is I will move the fault to the transmission line, okay? Um, to be honest, if you are a protection person, you must realize that having the fault at the bus bar is something that is hypothetical, and the way that the fault was removed from the bus bar, that was magic. I mean, in real power system, if we have a fault at the bus bar, all the circuit breakers connected to the bus bar, they must open to extinguish that fault. But in the previous case, we used a three-phase fault, and that three-phase fault was a magic three-phase fault. The three-phase fault appear and suddenly disappear. It's like an arc that appear and suddenly disappear. Now, in this section, I will consider again the three-phase fault, a volted three-phase fault, but in this case, we are considering that the fault is happening in the middle of the transmission line, okay? This discussion about the location in the middle is just because it's very simple to put the number together and show numbers for my students, okay? However, my students, they are top expert on matrix method applied to power system. That means if I move 75% to the right or 10% to the left, they are able to solve that problem, okay? Well, again, we have a pre-fault condition or before the fault. We have a steady state condition. There is a mechanical power going inside that machine, and the machine is delivering some electrical power, okay? Now, I believe you can see that I am using a subscript, and the subscript is a number, using a Roman number, and that is before the fault, okay? Because the impedance before the fault is defined over there, okay? Good. But then we have the short circuit, and now we have the short circuit at the middle of the transmission line. There are two important consequences over there. The first one is that this generator will still sending current. Some currents will go to ground here, but there are some current that will move across this and reach the infinity bus bar. Okay, that is the reason that this case is quite interesting. This case, the disturbance is in somewhere on the middle of the transmission line. And because the disturbance is at the middle of the transmission line, we have power transfer during the fault. We have a healthy, we have a healthy transmission line. All of you can see that we have here this healthy transmission line, and as consequence, there is possibility that some power must go through this line and then go to. However, of course, there are some power that is going to the fault. Okay. My student must recognize that it's possible to solve this problem, very simple, because they will be able to identify that this is a beautiful delta connection, okay? Um, okay, but coming to my explanation, what I'm trying to say is that during the fault, there is some power that is transferred to the power system, okay, to the infinity bus bar. There is some power that is transmitted to the bus bar over there, and there is some reactance, okay. I will not demonstrate this. My students can do it when they are solving some problems, but the reactance during the fault tend to be higher than the reactance that we have when the system is before the fault, okay? I will not discuss this because I don't have numerical example to show you here, but you must understand that, okay? Then this is an example that is more realistic because in real life, faults tend to happen at the transmission lines. And if we have the fault at the transmission line, of course, the circuit breakers that they are connected, the overcurrent protections and the distance protections, they will see the fault. And as consequence, they will open the circuit breakers associated to that line, okay? Right now, then we have this transmission line out of service. As a consequence, the power system will keep working in emergency conditions because it was a contingency. The power system is working um, at some emergency status, and the system will be delivering power to the infinity bus. Okay. What I'm trying to tell you is that right now, after the fault, the system will keep providing electricity, but again, the equivalent reactance between the generator and the bus bar change. And now it's clear, you can demonstrate this, that after the fault, the reactance is also bigger compared with the during the fault, okay? Well, now we are planning to use the equal area criteria to assess the transient angle stability of this case, okay? As you must be aware, we have three different situations. We have before, we have during, and we have after the fault, okay? We have three different conditions. What I will do now is show you that again, we have two areas. In this condition, in this three-phase fault with power transfer during the fault, we have three different power angle curve. Okay, you can see three different power angle curve, and it's clear because we have condition before the fault, and then during the fault, and finally, if everything is fine, we go after the fault, okay? What I'm trying to say is we have three curves because we have three conditions. We have three changes on impedances. We have three PQ curve, okay? And every single one is defined by this equation, power angle equation, power angle equation, power angle equation. Why this one is bigger than this one and bigger than this one? Well, I remember that I told you about the relationship between the reactants, and of course, that have an impact on the maximum power that you must transfer. You can transfer, okay? We have three curves, we have three different status, okay? But we want to apply the equal area criteria, okay? We will start here from the point A. Everything is fine. There is no fault. We are in a steady state, but suddenly, boom, short circuit. There is a short circuit, and the machine, the impedance between the machine and the infinity bus bar is increased so much, and the maximum power change. Then the machine will accelerate. The machine will accelerate, but suddenly the circuit breakers open. There is one transmission line that is removed, and again the reactant change. Now the reactant change, and then we are moving in this way. I mean, before the fault, we are at the point A. During the fault, I will move between B and C because the machine is accelerating. And that is the reason that the area A1 is a accelerating area, okay? And then we clear the fault by opening the transmission line, and as a consequence, the equivalent reactant change. As the equivalent reactant change, now we have another power angle curve, and then the machine will oscillate. And if everything is fine, this will be the final operating point. Okay? That will be the final operating point if everything is fine. Let me clean here a bit, and I will show you where is the final operating point. The final operating point is after the fault, okay? The intersection between the curve of after the fault and the mechanical power zero, okay? If the system is stable, that red dot over there should be the final operating point, okay? Okay, now is time. My student must be able to write the integral defining those areas. And if we want stability, what we need to do is the area 1 should be equal to the area 2. If we can find that, the system will be stable, okay? If we can identify a critical angle that allow the area 1 equal to the area 2, the system will be stable. Okay? What I will do now is I would like to show you this is the equal area criteria, okay? The equal area criteria is quite important because allow you to get delta critical, and delta critical is, for instance, defining what is the maximum angle that you can open the circuit breaker of that transmission line and the system recovers stability, okay? Okay, good. But in real life, we are doing something like this. In real life, what you have over here, this is a real system, okay? This is the data that I use for those simulations. If you want to reproduce the results, you can do it, okay? At home, no problem. But what I need that you focus is on those colors that I use for the plots, okay? What is this? Well, 0.2 seconds, 0.4 seconds, those times represent the time to open the circuit breakers of the faulted line. I mean, for instance, the blue colors say that I spend only 0.2 seconds, 0.2 seconds to open the fault, okay? Assuming that the fault is happening here at 0, okay? Well, as you can see, if I open this breakers quite fast, the angle is oscillating, but the angle is just oscillating very small. But what's happened when we start to increase the clearing time? Well, if you start to increase the clearing time, you will realize something quite interesting. And in this area, I believe you can see that in this area, the angles start to take off. The angles start to increase so much, and as consequence, the system become unstable. What I'm trying to say is there is a single number for that time that define the limit of stability, the stability limit of this power system. What I'm trying to say is it's very important that you understand that when we have a fault, that fault must be clear and must be clear before the system lost the stability. From the power system side, we want that, and we try to do our best to avoid the instability. But from the protection point of view, you must know that number in order that you must be able to trip your fault uh, without making the system unstable, okay? Here also, I want to show you those are the plot for the rotor speed of those generators, okay? I believe you can see something quite interesting. If you remove the fault at 0.2 seconds, if you remove the fault at 0.2 seconds, you have this oscillation on the rotor speed. It's quite, I love that oscillation, it's quite good. It's decreasing over the time and so on. But if you keep the short circuit forever, you can see how the rotor speed also is taking off. I mean, um, you must be careful with the clearing time. If the clearing time goes beyond the critical clearing time, your system will lose stability, and losing stability will be basically two important things. The angle start to increase like a crazy, taking off like a jet, and also the rotor speed. Okay.